Hello, my name is James and I'm here today to present to you our paper for the WASPA 2023 conference, Compressing Audio CNNs with Grass Centrality Based Filter Pruning. So ever since their introduction in the late 70s, CNNs have provided a very useful way to apply automatic feature extraction in a way which doesn't require as many parameters as just learning every single connection by using things like parameter sharing. And we can see that these are actually widely used in several problems, not just in the audio domain, but in the audio domain in particular here. And they're used for acoustic event detection, audio tagging, acoustic scene classification, and many more problems. So typically CNNs consist of convolutional layers, pooling layers, some different auxiliary layers, some nonlinearities. Particularly, we're interested in the convolution layers because they require the most operations to perform. They're based on the mathematical concept of a convolution. So minimizing the parameters in these layers is of the most important to us. So here's a little bit more of a visual example over what's going on. So our kernel matrix is applying basically a masking to our input data, and we receive a feature map, and we normally have several kernels for each convolution we apply. Typically they can be quite large, especially production models, like PANS is a very common one, and it's over 21 gigabytes in max. They're very resource hungry as well, so they require a lot of CO2 emissions. And when you deploy a large CNN, you're not just running it once, you're training a CNN to train over and over. So it's not just a training time issue, it's also a runtime issue, a production issue. You save a little bit on running something a million times, you saved a lot. So pruning is very important for this and energy efficiency. It's also very impractical sometimes to deploy some medium-sized models on very low resource machines. So it also brings the feasibility level down for what size models you can deploy on Internet of Things devices. And there are several examples over to where neural networks contain a lot of redundant information in them. So these are pieces of information which result in the same information further downstream. So if you've got a particularly deep neural network, this can cascade. And in fact, sometimes what you have in particularly deep neural networks is that redundancy added earlier, performing the same operation again and again in your tight neural network, can end up adding more noise and more variation into your network than actual benefit. And this can actually cause quite a big problem in learning and inference time. So in our work, we look at the filter pruning problem, which basically tries to take a convolution. If you substitute a layer in this convolution with fewer filters by this factor P, so we have less filters, we remove some filters, we want to maintain our performance. So our performance after substitution is not that far from our performance originally, and we have less filters, so it's more resource efficient. For another slightly more visual interpretation, here you can see that we're just removing a filter map, and the pipeline of how we perform this is we take our original CNN, we apply a pruning framework, and we apply fine-tuning to the prune network after the fact. So there are two main methodologies to achieve this pruning. There are active methods and there are passive methods. The active methods are data dependent. So for example, you remove a filter, then you evaluate the performance of your network, and then you take an iterative approach like this. You keep judging, okay, how does the removal of this filter affect the performance of our overall network? There are feature map based approaches, which generate a feature map and then uses statistics and rank energies, and it's in a similar way to the performance based. It's computationally expensive, and these require a lot of time and also a lot of energy, which sort of mitigates the whole point of removing these features. So the approach that we prefer to take here is a passive method, which is data free. They require significantly less energy, time, resources. Many approaches to filter pruning in passive sense will first embed their filters into a vector space. We instead take the approach that we embed our filters into a graph space. And to do this, we calculate the cosine similarity of an approximated filter. And we do this for each filter and each filter pair. We actually get an embedding where each edge of our graph here represents the cosine similarity between the two filters, which are now embedded as nodes. Some existing methods can be thought of in this new domain of a graph too. There's one which I can explain quite easily in this new graph domain, where given this setup where every edge is a cosine similarity, one existing method will look at which edge is the shortest, so which two nodes have the least in common, and then it will, at random, pick one of these nodes and remove it from the filter space. So this sort of approximation will remove nodes that are redundant, but is it removing the node that is the least redundant? Is it removing the node that has the least impact total on the network? And I don't think so, and this is one of the improvements that we propose. So thinking about why this approach is not optimal, we decided to think about what would be optimal. We came up with this heuristic. So this heuristic basically says that the sum of the similarity for every single filter should be minimized under the conditions that we have p% less filters. And of course, we can then draw the equivalents to our graph-based embedding, where we want to minimize the weight of the edges, so the total sum of the edges, where we remove this many filters, which is how many filters we want to remove, under this new function, which is a subgraph function. So once we remove a node, we also want to remove the edges, so we apply this new subgraph function instead of applying this removal. And the subgraph function is actually quite a complicated one to calculate, especially if we're removing p different items from it, or p% p of f. So we work it out based on a heuristic of, okay, how important are nodes? And in graph theory, there's actually a group of functions or a group called, or methodology called centrality. And centrality-based approaches is what our paper is based off. And the centrality will give each node a score, which we've got here, and this score is what we'll use to approximate the weight, and then we will remove n all in one go, approximating this argument function. This is a NP hard problem, so we have to use some kind of approximation, and judging the importance with this new heuristic, even though this is originally a heuristic, we've got a new heuristic, is the way that we approximate in our paper. So the first approach we look at is called weighted degree of centrality. And essentially all this does is it sums up the similarity that a node has to every other node in the graph. So it's a sum of all its edges, and that's the score that's given to each node. And then we just remove the one with the highest scores, so have the most redundancy. And this equates to this approximation to our function here. And of course, the only thing that's different between this and this function is we drift after this approximation here. So if we're removing one item, then our approximation is equivalent here, which is what we like to see. However, the more nodes we remove, the more we drift, more potential we drift from this approximation. Since we are removing the edges all in one go and not seeing the impact that removing one node has on removing the whole network, because obviously these nodes have neighbors in common, which may have an impact further down the line, especially when you're removing a large number. It may be no longer optimal and it may be a worse approximation. The second centrality-based approach we look at is called betweenness degree centrality, and this is a bit different to weighted degree centrality. So the idea here is that between any two nodes in the network, there is a shortest path between them, where obviously the paths are the sum of the cosine similarities between every node in that path. And what this basically says is, if a node is similar enough to another node, then it will be in the shortest path between them. And then the node in between and any nodes in between will have more in common with the those filters than those filters have with each other, meaning the filters in between would maintain more redundancy. So those filters get a higher score. And betweenest degree centrality looks at the sum of the shortest path between any 2 points. We sum it and we remove the points with the highest number. And here you can see it formulated where this represents the shortest path given it passes by the node in question. So this approach does actually have a worse approximation originally to this function. However, it drifts less slowly because we have a more intuitive grasp over what would happen to the rest of the network once we remove this node, rather than an egocentric point of view. So for this D-case network, which is quite a small network, we can see that compared to the similarity-based approach, which is the pairwise removal approach, and these other these both norm-based approaches, we perform the same as this GM method for between a centrality, but for weighted degree centrality we perform better than any current passive method, and quite close to this active method, which still requires a large number of filters in storage, so it doesn't necessarily solve the filter problem, and also requires a lot of parameters, and training time is long. So that was an example of a small network that we want to make even smaller. But one of the key applications to this kind of work is for large CNNs, which we want to use again and again, where the active methods, they become more and more unfeasible because you're trying to train on billions of parameters rather than, a few parameters. And we see here that our model actually, from unpruned to pruned, only taking away 25% of the networks, we have a performance increase. So not only are we removing the nodes, there's actually so much redundancy in the deep neural network, in the later layers, as I mentioned earlier, that the network has propagated down so much error that there's too much noise being added by these nodes. These nodes are so redundant that they're adding noise to the network. The noise in the computation is more impactful than the actual information we're getting out of them. So it really shows that it's very key for performance as well as size and as well as time to run. So running this with this much, 25% less parameters, is obviously going to be 25% less energy used in this case. And we can see that our proposed method outperforms compared to the pairwise similarity norm-based methods, GM, L1. Particularly, the performance gain is faster as well when filters are pruned using the proposed method. So we don't only get there, we get there faster, especially at the beginning of training, which is nice to see. And here is our summary of our findings. So our future plans is to look holistically at the impact of machine learning as an environment, achieve more model pruning, more data pruning, using very different methods, looking at improving passive methods, seeing if our passive method is optimal, trying to work out, is our optimal pruning heuristic optimal? It seemed to be one of these sort of trial and error things. We thought this logically seems like it should be like a good heuristic to use, and then it turns out it's better than existing methods, but is it optimal? Being better doesn't mean it's optimal. So this is something we're still looking into and looking to work out exactly, what heuristic is best to use. Is it different for different types of networks? And that sort of thing. So yeah.